We present SCVP, Learning One-Shot View Planning via Set Covering for Unknown Object Reconstruction. To obtain a complete 3D model of an object is important for many autonomous applications. Active reconstruction has been widely studied because it can automatically reconstruct a prior unknown object based on robots. For better performance, we focus on the most challenging view planning problem in active reconstruction. The aim of view planning is to find an optimal view sequence that fully covers the surface of the object. Existing view planning methods rely on stochastic state analysis or pre-learned knowledge to obtain the next best view after each robotic scan. However, this iterative pipeline does not allow for global path planning. That is, the robot can only plan a path to the next view in this iteration. On the other hand, mainstream volumetric methods may have a time-consuming inference and scene updating stage for NBV evaluation. We seek a one-shot method to obtain all needed views for small object reconstruction in a tabletop scene. This scenario sets a bound to estimated object geometry, which makes a non-model-based deep learning approach feasible. From the perspective of the application, it is well suited for a manufacturing line. Here is the overview of our one-shot view planning method. The SCVP network takes the volumetric occupancy grid as input and directly predicts an ideally minimum number of views that cover all surface areas. We plan the global path to traverse these views and register the point clouds to obtain the object model. We first formulate the model-based one-shot view planning problem, which can be considered as the set covering optimization problem. It is an NP-hard problem that aims to find the smallest subset under a set of candidate views. We use Gurobi optimizer to solve the integer linear program version in an acceptable time. Therefore, the supervised pairs can be automatically generated by making pairs of the input octo map and the views solved by SCOP. We proposed a deep learning-based approach to generalize the SCOP to those novel objects. We next present the network architecture and loss function of the SCVP. 4 convolution-based blocks are used to extract features at different resolutions. We concatenate features and put them in 5 continuous fully connected layers. Since views needed for object reconstruction are more important than unneeded views, we propose to balance it by a hyperparameter lambda. For each view score, we keep the views of whichever score is greater than a hyperparameter gamma. We last present the robotic path planning under the obstacle of the bounding sphere of the object. For convenience, we plan a straight local path between any 2 views and let the robot go around the obstacle. The global path planning problem is to find the sequence whose total local path length is minimized. This problem can be regarded as finding the shortest Hamiltonian path. We use state compression dynamic programming to solve it. We trained SCVP with a set covering dataset built from a set of scanned object 3D models. We split these models for training and novel testing. The code and experimental video are available online. We generate 35,328 supervision pairs in total. Here, the loss, precision, and recall are reported. As the SCVP has 2 hyperparameters, we select the value by the largest F1 score. 3 state-of-the-art methods were chosen for comparison. To give an intuitive result, we compare the planned path and reconstructed point cloud model on a motorcycle object. We used 2 indicators to quantitatively evaluate the algorithms in simulation. Our SCVP network can achieve lower movement cost than the other methods with similar or better surface coverage both on the trained objects and the novel objects. In real world, our method can avoid ineffective scene updating, raycasting, and movement, thereby achieving faster reconstruction of a complex object than other methods. However, the SCVP has the limitation of completing the pre-planned trajectory. Another limitation is that the SCVP reported failure cases under some rotations when the candidate views are small. To sum up, we generalize the model-based NP-hard SCOP to non-model-based view planning by deep learning, propose the SCVP network, and provide a highly efficient object reconstruction method. It is of interest for studying how to expand the view space and be biased towards starting from the best views in future. Thank you.